Hello, it's Keith here. This is lesson 7 of my Z80 tutorials. So we've got quite a lot of interesting things to go through today, so let's go ahead and make a start. So let's begin. Now the first thing we're going to look at is RSTs. What an RST is it's a call to a byte with a memory address within the first 64 bytes of memory. Now let's have a look by example. So let's start then with just a very simple program. So org and 8000, RST 0 and ret. Okay, and we're going to put a breakpoint at the very first command and we'll just assemble and we'll see what the RST command actually does. So I'll just bring that in there and we'll start our program now. So here's our debugger here and you can see it's calling RST 0, and if I just do F7 to step ahead, you'll see we've actually ended up at memory address 0000. Okay, and you can see here in the stack the return address is the following byte along. You see the RST command is a 1 byte command, whereas a normal call would be 3 bytes, the call command and the 2 byte address. The RST command is just 1 byte. So that's RST 0, and let's do RST 1 and we'll have a look at that. Okay, so here's RST1, which is also sometimes called RST08, and there's a very simple reason for that. This jumps to memory address 0008, and there were 8 in total from 0 to 7, and if we have a look here, you can see the memory addresses go from 0000 to 0038 in hexadecimal. And it's this RST7 we're going to be interested in today. Because what are we going to do today? Well, we're going to create our interrupt handler. So in the past, interrupts have been running on the system at all times, but before we've been letting the firmware take those interrupts and do whatever it wants with them. But there's some reasons we will want to use those we will want to handle those interrupts ourselves, and we'll be looking at that today. So as I said, an interrupt will typically call RST7. That's always the case when we're in something called interrupt mode 1, and you can see we are here because you've got a number 1 here. There are 2 other interrupt modes. Interrupt mode 0, which has some very unusual functions that I don't think there's any reason you'll ever need to use. And there's another mode called interrupt mode 2. Now, interrupt mode 2 is quite hard to use and it isn't very practical, but unfortunately, because handling interrupts ourselves requires us modifying these bytes at hexadecimal address 38, we can't do that on systems that have ROM at that address, where we can't get any RAM in place, and that's true on the Spectrum. So on the Spectrum, to write our own interrupt handler, we have to use interrupt mode 2, and we will look at that in a later lesson because it is unfortunately quite complex. So anyway, the commands to switch interrupt mode are very, very simple. You just type IM0, IM1 or IM2. Now, the Amstrad CPC, the MSX, and in fact all of these systems are always in interrupt mode 1 by default, so you'll never need to set that. So I was just telling you those for your information. Now, today's lesson we're going to create an interrupt handler for the purpose of doing a timed event. But there is actually another quite important reason you will want to consider using an interrupt, writing your own interrupt handler on the Amstrad CPC, and that's because it allows us to take over all of the control of the system away from the firmware, and this frees up resources for our own use. Now, the first resource it frees up is performance. The interrupt handler on the Amstrad CPC does a whole variety of tasks. It updates timers, it reads the keyboard. Now, we may not care about the keyboard, and we certainly probably won't care about it updating its own internal timers. So by writing our own interrupt handler, even if that interrupt handler just contains a return command at address 38, then we will save some performance. But beyond that, it allows us to gain access to some register resources that the Z80 has kept kind of secret from us, that up until we were able to do our own interrupt handler we were not able to gain access to. And the main one of these is the shadow registers. Let's have a look at them now. So if we press F7 here, you'll see here are the normal registers we've used before, but there's these extra registers over here. Now they're not very clear here, but you can just see there's 4 of them here. And if I bring in the web page, my web page, which I suggest you visit after you finish watching this lesson, you'll see there is a second accumulator, a second flag register, and a second copy of HL, BC and DE. Now, let's just put in let's just change this, and I will let's have a look at another command now. Now, there may be times when you need the interrupt handler to execute immediately, and there's a way we could, well, if we literally wanted it to happen at any time, we could just put in an RST 7, and that would call the address that is the interrupt handler on the Z80. But if we want it to occur at its natural timed occurrence, what we can do is we can do a command called HALT. And as long as interrupts are running normally, this command will run indefinitely until the interrupt handler occurs, and then execution will continue at the next command. So if we just do an assemble here, and then do call 8000, you can see execution is now sitting on that HALT command. And I'm just holding down F7, so you can see that the processor is ticking away, but execution is not moving from that HALT. So let's cheat a little bit. And here is the address 38. Now this is what the Z80 will call when that interrupt occurs. So we'll just press F7 there, and if we close this, we'll just remove this breakpoint, and then we close this. Now you'll see we're now at the interrupt handler, and if we step in, you'll see the first thing it's doing is disabling interrupts. DI disables interrupts, and that's to make sure another interrupt can't possibly occur. So interrupts are now disabled. You can see that because of this tick box has been removed here. And then you've got this command EXAF, AF apostrophe, and that apostrophe marks that this is the shadow register, which is the register over here. Now if you look here, AF is 0068, and when this command executes, you'll see that the normal register and the shadow register have swapped over. And so what this has done is given us an extra, it's given us a fresh accumulator and flag register for our use. And now it's going to run this EXX command, and what this does is it swaps HL, DE and BC with the shadow versions as it just did there. Now why is it doing that, you probably think? Well, the interrupt handler can run at any time during our normal program, provided interrupts aren't disabled with the DI command. Now what that means is the system is going to have some resources to process the interrupt, but it's not going to want to waste too much processing power while it's doing that. So you could do a series of push commands to back up all of the registers that you need to use, and then pop commands to restore them so that execution continue with whatever it was doing before the interrupt occurred. But that would be quite slow. But so what the Amstrad CPC does is it uses these shadow registers to quickly bring in some alternate memory so that the firmware interrupt handler can work, and then swapped it back again so that the normal registers can continue operation. So that's what the Amstrad CPC does. So let's just continue its execution there, and everything just returns back to normal. Now there's some more things we need to sort of discuss here. Firstly, interrupts are the Z80 isn't causing the interrupts. The interrupts are being caused by the other hardware attached to the Z80, and the important thing you need to take away from that is the way interrupts work is different depending on the computer you're working on. So for example, on the Amstrad CPC, the CPC hardware interrupt comes from the video system, and the interrupts occur multiple times per screen refresh, and in fact they occur 6 times at what's 300 Hertz. Whereas the other systems you'll typically be working with, they only occur once per refresh at the bottom of the screen or the very top of the screen, depending how you want to look at it. So the Amstrad CPC refresh occurs 6 times for every 1 time that the ZX Spectrum or the MSX's or the Enterprise refresh occurs. This refresh is very handy for us on the CPC because it allows us to do tricks where we change the color palette while the screen is redrawing, and that's how my Chibi Akuma's game gets more than these typical 4 colors on the CPC's Mode 1 4-color screen. The problem with that is that these interrupts are happening very often, and on the CPC they're happening 6 times more often than on the other systems, and I think that's why on the Amstrad CPC they're using the shadow registers to free up those extra registers that the interrupt handler can use without worrying about restoring them when process returns to the normally running program. But on other systems, other systems may not affect the shadow registers in the same way. As I say, it's only really the Amstrad CPC that really uses everything. The ZX Spectrum does use IY, so again, depending on the system, you do have to be a little bit careful, and the best thing to do if you want to use all of the Z80's resources is disable interrupts and back up everything that the firmware needs before restoring them, or write your own interrupt handler. But again, as soon as you re-hand control back to that normal firmware interrupt handler, assuming you do, you need to make sure whatever it relied on being in place is back in place, otherwise it will probably crash or behave erratically. Now on the Amstrad CPC, the shadow registers will all be corrupted, but so you can't let it into normal firmware interrupts occur while you're using the shadow registers, but provided you restore BC of the shadow registers, once you enable interrupts, the firmware will continue to run. The BC shadow register actually contains the screen mode settings, and it sends that BC directly to the hardware. So if you've changed it, this firmware interrupt handler will corrupt the mode or crash the computer. As I said before, the Spectrum uses IY, but to my knowledge, the other ones are pretty much okay. So you can use the shadow registers without worrying about what the firmware is going to do to them. It won't change them. You'll be okay. Now, what are the shadow registers? How are the shadow registers going to benefit us? Well, unfortunately, they're quite hard to use effectively because you've got sort of only two options. You either swap the accumulator or you swap all three of the other major registers. And because you're swapping all three of them, you've kind of lost any data you were planning to work with, because they're now all in the shadow registers and you can't gain any access to them. Your only access to the shadow registers is to swap them in or swap them out, and when they're swapped out, you can't get to them. Now, if you wanted one, you might think, well, I could push it onto the stack and then pop it off once I've swapped in the shadow registers. But the amount of time you'll be wasting doing that kind of thing kind of nullifies any benefit you could gain from using the shadow registers. So in my Chibi Akima's game, what I've used the shadow registers for is things like the bullet loop, where the bullets are being drawn, and then there is an execution for the collision detection. Well, the collision detection is kind of its own standalone code. So I swap in the shadow registers, use the shadow registers to process the bullet collision, swap the registers back, and then carry on with my loop. So I can save a few pushes and pops because I'm doing that totally separate command. But the Chibi Akima's interrupt handler doesn't protect the shadow registers in the same way as the CPC one doesn't. So it does mean that I have to disable and enable interrupts during that period. And we do that with the DI command to disable interrupts and the EI command to enable interrupts. Now the catch with that is while interrupts are disabled, if the 1/6 line refresh occurs and Chibi Akima should change the colours, if the interrupts are disabled it can't, and so it will be delayed until it entirely re-enable interrupts. And that's why if you watch the game, sometimes you'll see the colours are juddering slightly and aren't in a very consistent position. It's because of my disabling and enabling of interrupts. Now, again, as I said before, interrupt handling is very hardware specific, and on the Amstrad CPC the interrupts occur naturally, and if they occur while interrupts are disabled, they will occur immediately as soon as interrupts are re-enabled. However, on other systems that may not be the case. On the ZX Spectrum, if you miss an interrupt because interrupts are disabled, it will just be missed, and this can cause problems with if you're updating your music on the 50 Hz interrupt and you miss one, the music will start playing much slower, more noticeably more slowly, which could be a problem. On the flip side of that, systems like the MSX and the Enterprise, you actually have to tell them during your interrupt handler, I've processed this interrupt, be quiet about it, because if you don't, the interrupt will fire immediately as soon as you return from the interrupt handler, over and over and over again, and your music will play super fast and things. So depending on the system, what you have to do, it does vary, and I've tried to document all of this on my website, so please take a look there. So we've got the HALT command to wait until an interrupt naturally occurs, the disable interrupt command to stop interrupts from occurring, and the enable interrupt command to restore normal procedure. And then we can always call the RST 7 command if we want to simulate an interrupt, but that would occur at the wrong time. So that's basically interrupt handling. Just to summarize, interrupt mode 1 calls to 0038 when the interrupt occurs, any code we put there will be what happens on the CPC, 300 times a second, on the other systems 50 times a second. So that's kind of how we work with the system. Now we're going to use this today to actually create a kind of simple version of the color switching code I use in Chibi Akumas, which allows you to get more than 4 colors on a 4 color mode screen. We do need to learn another command to do this though, because to do this we actually have to interface with the hardware, and so this is going to be the first time when we learn how to actually communicate with hardware devices other than the screen, which is of course accessible from the normal memory. So to try and describe this, I've created a quite nice little picture using all of my artistic skill. I've really created something I think will impress you. And here it is in Microsoft Paint. So, I apologise, it's best I could do. So the Z80 processor is here on its own, and then connected to the Z80 are various devices, and you can see I've kind of done some examples, and these aren't representative of the way it really works on the Amstrad CPC or any other piece of hardware. They're just examples of the kind of thing you might see. And the way I'd suggest you think about the hardware connected to the computer is try and think of a telephone exchange where each device has a phone number, and this phone number can be 0 to 255. And the way it works is that the devices can't call you. You have to call the device by calling its phone number or its device number, and then you can either call it and give it a message, and the message will always be 1 byte, or you can call it and you can receive a message of 1 byte, but you have to make the call. And the way you do this is with an out command to going out to the device. So if we were out device 200, we would send it 1 byte, and that would be the disk in this example. And if we were to in a byte, we would call it on our device 200 and we'll get 1 byte back. And as I say, things that you might interface would be the screen, the disk system, the controllers, the keyboard and the joystick, the sound system. And you're probably thinking, well, why would I out to a joystick? A joystick can't send me data, it can't receive data. But that's actually not true. You see, often, firstly, the joystick, the keyboard, and often the sound card will all be sort of combined into one device. And also, when you're doing a keyboard, for example, you actually have to tell the keyboard, I want to receive row X of the keyboard keys, and it will send you back. And when you call back and say, right, well, what's the settings of that row? It will give you a byte back that says, well, this key's down and these other ones are up. So it can be quite unusual how you work with the system. But as I say, you need to think of it as these separate devices, all of which have a number, and you have to call that number to either give it a command or to receive one back. It won't call you with its information. And we do that with the out and in commands. Unfortunately, again, as I said before, we're definitely into the area of hardware specific, so the computer you're working on could work quite differently, and this is a time when it does get a little bit crazy. So some systems like the MSX and the Enterprise, they use an 8-bit bus for their I/O, and what that means is the hardware has a number from 0 to 255, like in the example I've given you here. But on the CPC and the ZX Spectrum, it's actually 16-bit, and rather confusingly, the commands that you will put into your assembly do not represent this. I know that sounds weird, but let me give you an example. So a typical command for an out would be out C, A, and this would be sending the message A to the device in the register C. Well, that looks very sensible and normal, you think, and yes it would, and that would be exactly what it does on the MSX or the Enterprise that use this 8-bit I/O bus. But unfortunately on the CPC and the Spectrum, the Z80 doesn't actually do what it looks like it's going to do. What ends up happening is out BC, A, and you cannot, in WinApe at least, you cannot actually compile out BC, A, even though that's the command it's doing. And this caused me a lot of confusion in the early days, because I was seeing examples that were setting B and C to different values, and then nowhere in the example could I see where B was being used. And the reason was because of this quirk, and it took me ages to find out, and it actually caused me some quite serious problems, and I will cover that in just a second. But just just because what I'm explaining is so confusing, I think this is a perfect time for me to point out a resource that you will want to get if you really want to dig into this kind of thing. It's linked on my website and it's free to get from the Zilog website, and it's the Z80 user guide. And here it is, and here is the page on the out command, and all of this is clearly documented. You see here it says about A0 to 7, which is the first 8 bits of the address, and then it says register B is placed on the top half of the address bus at the same time. And this really, when you get confused with this kind of thing, when you really want to make sure that what you think is true is definitely true, going to the Z80 documentation is absolutely the thing to do, because it's surprisingly easy to read as a sort of relative novice, and it's free, and it does explain all of the really tough stuff when you're not sure exactly what's going to happen. And there's been a few times I've been able to confirm what I'm doing is correct because of the of this documentation. So I definitely recommend you get that and put it in your collection, even if you don't often need it or don't even ever need it. You definitely want to know about it, you definitely want to have it. So that's the Z80 guide, and that's this rather odd out command. Now, I said about it caused me some trouble, and I will explain why. Now, the out command, sometimes there will be cases where you want to do a lot of out commands in succession, and there is a command for this. Like the LDIR command, which loads and increments, there is an out and increment command, OTIR. However, unfortunately, this command uses B as a counter. Now, on the CPC, that B that's being used as a counter is actually part of the IO bus address. And because it's changing as you run the command, it actually starts spewing data to random addresses on the system, and it can cause some quite crazy results. And the crazy result it unfortunately caused me is when I set all the colors to red, it actually overwrote my floppy disk and corrupted it. Now, there is a way around that, and we'll have a look at that later today. But as I say, the important thing to take away from this is on the MSX you can use all of these commands without worrying too much, but on the CPC and the Spectrum, these commands like this do not work properly, and you have to be very careful if you use them and know exactly what you're doing. Now, as I say, the Amstrad CPC address bus is 16-bit, and that's confusing enough, but I'm afraid it gets even worse. The devices connected to the system, such as the gate array that handles the screen, doesn't have just one address. It has multiple addresses. It kind of scans an entire range. So I think with the gate array, the graphics, for example, if you set BC to anything from 7F00 to 7FFF, it will actually, the gate array will receive it and process it. And this can actually mean sometimes you might be sending to the completely wrong address, like in my example where I overwrote the disk, and it will still appear to work fine, but it could be causing all kinds of terrible problems. You're probably thinking, well, this sounds awful, this is going to be really tough, what do I do? And the answer is quite simple. You go online, you find an example somewhere that works, and you copy that. That's all you do. And what you do is you get your code working with your example code you found, you put it in a nice call, and then you just leave it to that. Now, in Chibiakamas, I don't ever access the disk system without commands. It's not worth it. Just rely on the firmware to do that for you. It's too much work. And if you did access it directly without, every single disk system, every custom piece of hardware like the C4 CPC cartridge, you wouldn't be able to use because they use custom firmware. So don't do that. The graphics system, you'll probably play with it for a week, gets the right commands you want to use with the graphics, and then you'll never touch them again, and you'll just run the calls to that. Keyboard, I wrote some code mostly based on CPC wiki stuff, never looked at it again, never will look at it again because it works perfectly. So this kind of thing, you have a few hours of head scratching and then you get it working. And what my plan actually is I'm hoping to be able to give you copy pastable code examples of everything you're realistically going to want to do in your development, so you shouldn't really ever need to worry about how to work without. As I say, you need to know they exist, you need to know these quirks just so you don't mess with them and break them, but from the point of view of actually day-to-day coding, you will not work without because you just don't need to. For audio, you don't ever call the audio system, you just load in your Arcus tracker module and let that do it for you. so HALTs don't become a major concern on a day-to-day basis. So I'm just explaining them today, but don't worry about how hard they look, because in practice it's a rare thing you're going to need. Anyway, so let's move on. So as I said, we're going to use the Amstrad CPC gate array, which is the graphics system. Well, its primary role for our purposes today, the graphics system. It does have other purposes, and we're going to use it to allow us to get more than 4 colours on the CPC's 4-colour screen. So let's make a start with our actual coding. Now we've discussed all that quite confusing stuff. So we'll get rid of our code here. And the first thing we're going to do is we're going to disable interrupts with DI. And the reason we're going to do that is because we're going to mess with the interrupt handler, and we can't risk an interrupt occurring while we're making those changes because it could cause unpredictable results. So for safety, we disable interrupts. And then what we're going to do is we're going to load A with C3. And C3 is the bytecode for a jump command, and that's because the interrupt handler is going to jump to the code that we want it to process the interrupts. Now, you probably saw earlier, there's actually only 8 bytes at each RST, so you can't put huge piles of code there. Really, you're just going to put a jump or a few commands and then a call. That's all you really want to use them for. And I didn't really mention this, but the other RSTs, RST 6 to 1, they are, depending on the system you're working on, they may be free for your own use. And you can use them if it helps you to, as a 1-byte call command. You can basically save 2 bytes if you need to run a command a lot of the time. And on the systems, they may have special functions, like on the Enterprise, it actually calls system firmware functions. So as I say, you may want to actually use them for your own purposes in some cases. But anyway, back onto the code. So what we're going to do is we're going to load in 0038 with the jump command, and then what we're going to do is we're going to load HL with the address of what we're going to code as our interrupt handler. And we're going to load that 1 byte afterwards at 0039. And this is going to actually do our interrupt. That's going to program in our interrupt handler. We've done now, so we can turn interrupts back on and let them run normally. And what we're going to do now is just going to put a little infinite loop in, because we're not protecting any of the firmware's functions, and we're not going to restore the interrupt handler. We can't return to basic or it will crash. So we're just going to create a little infinite loop. And we'll put a HALT command in, just because we want to practice using that command. So we'll halt, that will wait for an interrupt, and then we'll jump back up here. So we're just going to wait forever and just let the interrupt run normally. And this return command has no purpose because we can't return. And then we're going to program in. We're going to start writing our interrupt handler. And the first thing we're going to do, we don't really need to do this because our loop has no code, but for clarity and for a bit of proper design, we're going to swap to the shadow registers. So EXX will swap HL, BC and DE, and then we're going to do EXAF with AF apostrophe. These 2 commands are slightly different, but their function is basically the same. This swaps the accumulator with the shadow accumulator, and this swaps the other main registers. There is no shadow version of IX and IY, so you will have to use push pop if you need to use those. And now what we're going to do next is we're going to load B with F5, and then we're going to use our in command. And if you remember, I said in will call a piece of hardware and ask it for some data, and it will give us something back. And again, this is rather an odd one because we're loading B, and as I said before on the Amstrad, we should kind of load B and C, but actually the piece of hardware we're talking to will respond to any address starting F5. So it's a little bit confusing. You could put in load BC, F500, it will work, but the examples all do this, and by only loading B, we're saving a little bit of memory and speed. So, and remember, this is going to run 300 times a second, so I guess we do need to save that speed, even if it's not very clear. So what we're going to do is we're going to do in A, C. And if you remember, I said what this is actually going to do is in A, BC. But I can't put that command in because it doesn't exist. This is the command that will assemble, so that's what we have to put in. And we're only interested in one bit of this, of the data we get back. I'll explain what it does in a second. So what we're going to do is we want the rightmost bit. So we're going to do RRA, which rotates it right, and the rightmost bit will fall off into the carry bit. And what is this device we're talking to, and what is this bit going to denote? Well, what it tells us is when the screen has fully refreshed. As I said, on the Amstrad CPC, there were 6 interrupts along the screen. And what we need to do is we need to check when the screen is fully cleared and is about to redraw anew, so that we can reset our raster colors, which is going to be our multi-color 4-color screen. So we need to reset when we get to the top of the screen so it's consistent and doesn't kind of roll or start in a strange place. So if the carry bit isn't set, then that bit was 0, and it means that we're not at the top of the screen. So we're just going to jump to interrupt handler. Okay, so we're okay to continue if that carry bit is not set. If the carry bit is set, then what we're going to do is we're going to load HL with the address raster colors. And this is going to reset raster colors, HL to raster colors. And now what we need to do is we need to copy this up here, and we need to set another version of this, but this version is going to be self-modified. So when we get to the top of the screen, we reset HL, but otherwise we're going to load it with this version, which will be whatever it was previously. So it's going to run every interrupt with a different version of HL, because, as I say, we're going to use self-modifying code to change this top version. Okay, so let's continue. So at this point, we're ready to start messing with our screen colors. And this first example is a very simple one, so we're only going to change the background color, color 0. And the way we do that is we load BC, because remember I said we need both bytes set, and 7F, which is the address of the gate array, which is responsible for the graphics. And then the next 2 bytes are going to be 0, 0, and that's because we're changing color 0. And then we're going to do out C, C. But as I said, this is effectively doing out BC, C. Okay. And our next thing we're going to do is we've got this HL, which is going to point to our raster colors. Let's just paste those in now, just so you can see them. Here they are. Now, these colors probably don't look like anything you're familiar with. They don't match the ones in BASIC, and this is a point where you need to look at my cheat sheet. These are what's called hardware colors. These are the sort of colors at the as they are known by the Amstrad's internal hardware. So you just need to use these kind of colors here to define the colors you want to use. So yeah, check the cheat sheet, and if you want to pick appropriate colors, then just go ahead. But in this case, we're just using 4. We're just using 6 random colors. So at this point, we've selected the palette we want to change. We're always going to change palette entry 0 at this point. And so now we need to load A from HL. And then we want to do out C, A. So we're sending the data we just read from the raster color array to the gate array, and that will set the color. And then we want to do inc HL, so that HL is pointing to the next color for the next time this loop occurs. Now, you remember I mentioned the self-modifying code, and what we're going to do is we're going to self-modify this line so that the definition of HL here is correct for the next color. So if we just do LD and then -2 here, and then HL. As I said before, if you were compiling this on a different assembler, you would need to represent this like this, because the way I'm representing them here, I find it a lot clearer, but I know a lot of other assemblers don't like it. But anyway, it's all the same. So we've now stored the new value of HL in this here, ready for the next call. And interrupt handlers, things that you're going to have to run very frequently, very fast, are the ideal time you really want to start hitting out the self-modifying and really tweaking your code until you can make it as efficient as possible. And things like skipping that one letter C here when you don't need to, when it's running 300 times a second, it will save just little bits here and there, and it will really start to add up. So the self-modifying code is kind of a must here. So we're going to do EXAF and AF apostrophe to get back to swap the shadow A and the normal one again. And then we're going to do EXX, which swaps the rest of the shadow registers. And then the last thing we're going to do is re-enable interrupts and return. Now you'll notice our interrupt handler never disabled interrupts, and that's because it doesn't need to. Interrupts are disabled automatically when it runs. So let's assemble. I've got a comma there, that shouldn't be there. Let's assemble again. And let's call 8000. And you'll see here, interrupts are actually disabled as soon as the interrupt handler occurs, so we don't need to disable them to make things work correctly. And you can see here, we've got multiple color splits. Now, we programmed in 6, but you can only see 5 here, and that's because the 6th one is actually completely off screen. But that is exactly what we expected to see occur. And because our code is never disabling interrupts and never doing anything else, you'll see there's absolutely no shake in the interrupts here. Whereas in the Chibiakuma's game I wrote, there is quite a lot of shake, and that's because of other commands like the sprite drawing that's disabling interrupts. But unfortunately, because we're never returning to basic here, our Amstrad is in an infinite loop and has basically crashed. So we'll just have to reset out. So we'll just do Control F9 there to reset. And that's our first example done. Now we're going to continue on with example 2. As always, you can download these examples from my website. In this case, I've actually combined them into one example. I'll just show it you now. So if you've downloaded it from my website, you can see the first example just by compiling it. If you want to see the second one, you just need to uncomment this line, and it will modify the code to do the second example. So that was just something, because this one shared a lot of code, I thought it was the easier way to do things, but I did feel I had to explain that. So now we're going to do our second example, and this time we're going to make a few improvements. Firstly, in the last example we broke basic. We couldn't return back to basic, and that's not great. As I say, if you're using disk systems, you'll probably want to use the firmware to handle your disk drive access for you, and so we need to pay some respect to the firmware for it to do that. Also, if you need to return to basic, you'll want to be a bit more careful. So let's learn about the things we need to do to keep the Amstrad CPC firmware happy. As I said, it will vary what you need to do depending on the system you're working on. In later lessons, I'm going to provide you with sample interrupt handler routines, and we'll learn more about them then. But for now, we're just going to look at the basic stuff on the Amstrad, because this thing about calling address 38 when an interrupt occurs in interrupt mode 1 is common to all of the systems. So this is really the primary thing you want to learn. So the first thing we're going to do is we're going to do an EXX. So this switch is in the shadow registers, and what we're going to do is push BC, because BC is the shadow register that the Amstrad CPC firmware needs to stay the same. The others it doesn't really care about, doesn't mind, but that BC cannot change. So that's the first thing we do. And then what we're going to do is we're going to load HL from address and 0038, and then we're going to push it. And then we're going to load from 3A, and then we're going to push that again. So what we've done is we've taken 4 bytes from the addresses we modified and pushed them onto the stack. And this is so we can restore the basic firmware interrupt handler later, and basic will never know the difference. It'll be perfectly happy. So that's why we've done this. So now we can modify we can put in our custom interrupt handler, and in basic we'll be quite happy. And then what we can do, it'll be down here somewhere, is we do disable interrupts again, and we do pop HL, and then we do LD and 003A, comma HL, and then we pop HL again, and we do load and 0038, comma HL, and this has restored our normal interrupt handler. And then the last thing we do is we do EXX, pop BC, oh dear, I keep typing a bit off, and then EXX again, and then enable interrupts, and then return. So this has restored that all-important shadow register for the basic, and turn interrupts back on and go back to basic. So this will be our end of our program. But we want to do a few more things as well, because we're going to do a bit more snazzy animation here. So what we'll do is we'll load HL with the address of the CPC screen at C000. We'll load D. We're going to use D as a counter this time, and we're going to load C with a bit mask. And the bit mask we're going to use is just 1, 1, 1, 1, 1, 1, 1, 1. So we're going to use this for an XOR command. And next, if we go into our infinite loop, which will not be infinite this time, but we'll just leave the label the same, we'll load A from HL. We'll do XOR C, and then we'll load HL with A. So it's going to flip all the bits in that just to give a bit of excitement. And we're not going to worry. We did some quite efficient code last time with regards to inking H and inking L separately. But this time, we're just going to keep it simple. We'll just do ink HL. And then we'll do load A, H, or A. And this is, again, checking if HL has gone over the FFFF boundary to 0. At that point, we've finished modifying the screen, and we need to undo something else. And what we're going to do is we're going to jump to a label called page done. And this is once we've filled the screen once. So page done is going to reload HL with and C000. And then it's going to do dec D, which is decreasing our counter. And if our counter is not 0, then it's going to rejump to inf loop. Okay. And once D equals 0, then we are going to return to basic. So it will flick our screen 10 times. Now, our interrupt handler is going to receive some upgrades as well. So this first bit is going to stay the same, but this time we're going to be a little bit more clever with our interrupt routine here. Now, we're going to keep this the same because we're going to set color 0 first, but then we're going to take all of this out all the way to here. And this time, if you remember, I sort of said about that OTIR command which malfunctions on the Amstrad CPC. So we can't use that because that would repeat. But there is a kind of cut down version called OTI, which is out an increment without the repeat command. And we can use this if we're careful. And we will be careful, so we will use it. And what we do, OUTI, which is the non-repeating version. And then, because OTI has broken B, because as I said it uses B as a counter, as a loop counter, it has decreased B, and we need B to stay the same, so we compensate for that by putting inc B. Okay, and that now everything is fine for that. Everything is fine for that OTI command to run again. However, we also want to do something slightly different as well. Here we set pen 0 to here we set the gate array to change pen 0, but this time we want to change pen 1. So what we're going to do is we're going to do inc C, and then we just copy this command here, and we will now be changing pen 1. And then if we do it again, that will change pen 2, and here we'll change pen 3. And this time we have no need to actually inc B again because we're not going to do that anymore. So we've changed pen 4, pen 3, pen 2 and pen 1 here. Very good. And then our last thing we need to do is save back to the raster color array here. So as I said before, the OTI command or the OTIR command will read from HL, and they will, instead of writing to DE like the LDIR command, they will write to port C or to port BC on the Amstrad CPC in the Spectrum. So they're going to read from successive HL addresses, and that means we need to modify there's not enough raster colors here anymore because we now need 4 times this, and we'll just paste them in. I've not used very good colors here because I'm just showing this as an example. So here you've got 4 colors. So this one here will be loaded by this one here will be loaded by this one here will be loaded by this, and the last one will be loaded by this last one here. And then HL will be saved, so the next time the loop occurs it will run from the next line, and you'll see we've got 1, 2, 3, 4, 5, 6 here, which is for the 6 raster interrupts. As I said before, the top one won't be shown unless unless something's delayed the system so that interrupt occurred at a strange place. But we put 6 in anyway. And so if we compile this, we've got no errors. And then if we do call and 8000, and we just remove that breakpoint, I don't know why that's there. Now you'll see we've got this cycling color command, this color thing. We'll just run it again, and the fact we can run it again suggests we have done everything that BASIC needed and the firmware needed to continue working normally. And anything we do now in that interrupt handler, provided we do those restores, we don't have to worry about the firmware breaking or the BASIC breaking. We've kept everything perfectly intact, and BASIC doesn't know the difference. The firmware interrupt handler, the firmware doesn't know the difference. And as I said, that's very important when you want to start working with disk systems. So you'll see you get this cycling effect between the colours. And what you want to do, if you want to pick more interesting colours, is you want to look at the cheat sheet, these colours here, and pick the colours you want, and just type in the hex values here. And as I said, the first one will be colour 0, and the last one will be colour 3. So there we go. So, but would you believe that's actually everything I wanted to teach you today? We've covered an awful lot of stuff, but we've covered it very, very fast. I think this is a perfect example of a good use for an interrupt handler, and also the perfect simple example of how to use the out and in command, but in a practical way that you'll really want to know. Now, as I said before, just copy this example or modify this example if you want to do something similar. You could read all of the documentation and check all of the port addresses, but once you get something that works fine, just go ahead and use it. Now, we did briefly mention the RSTs, but I just want to give you another sort of clear example of an RST command. So let's just have a go at that now. Now on the Amstrad CPC, RST6 is actually designated as available for user use. So what we can do is we can put our own RST handler there, and we don't have to worry about restoring it back for the firmware to work. So let's give that a go. I'm going to show you now how to do something that you quite often see in RST use, and you may want to do yourself if you are really trying to scrape every byte out of your system as you can, because as I said before, an RST call is just 1 byte, whereas a normal call would be 3. So there may be times where you really need that memory, and you just need to save that extra 1 byte. So what we're going to do is we're just going to put the same kind of code in as before. So we're going to jump to RST test. Notice that's not a call, that's a jump. So because we've only got 8 bytes at the RST address, we're going to do just a jump command there, and we'll put the rest of our code somewhere else where we don't need to be so restrictive. And what we'll do next is we'll do pop HL. And what this is going to do is this is going to get the address that called the RST out of the stack. And there's a reason we're going to do that. And what we're going to do is we're actually going to load in. I'll put in the example of what we're going to do first. That'll be more clear. So if I put in RST6 here, and then I do def is we're going to make RST test actually print a character to the screen. There's no practical use for this, but I just wanted a nice easy example. And so if we just change this to an A, and then what we'll do is we'll load A from HL. Now if you remember, we've just loaded HL from the stack, and it's going to be the next memory address that the return would occur once the RST had completed, which is this following byte from the RST. But what we're actually going to do is we're going to use that as a parameter for our call here to print char, and then if we inc HL and then do jump HL, what we've effectively done is we've skipped over this byte here and proceeded to the next command here. And we will just test this. So we'll put a breakpoint here, but we'll know if we've run that because we'll probably crash. And we'll just compile here. And if we call 8000, so you see we're now we're now at 30. We're going to call our RST here, and then we just jump to RST test. We pop HL, which is this 800C. We then load in A, which is 61, which is the letter A. We then call our print char. We don't want to see that because that'll be quite long. We then inc HL and jump HL, which gets us to here, skipping completely over this command here, which wouldn't have crashed, but anyway. And now we return. And we've printed an A to the screen. Now, the point I'm trying to make here is if you are really tight for memory and you need to pass a parameter to a command, you can create an RST and read in from the stack, the returning address, read in those bytes and skip over them. And it's this kind of thing that things like the Enterprise with its EXOS call are doing, and also quite pretty much all the other systems do it as well. The Amstrad even does it, and the TI-83 do it as well. This thing of having bytes of raw data after an RST call to make that call more practical while using very little memory. That said, of course, because we're doing because you've got so little memory at that RST jump address, you are wasting potentially quite a bit of performance if you're jumping around quite a lot. But I still think this is something you do want to know, and you do want to consider for times when memory is really short, because you may find it is really short. Okay, well, that's everything I actually wanted to cover this week, so I hope you enjoyed it. I hope you weren't too disappointed by my paint skills. If you want to commission me to do your network diagram in paint, please let me know. There'll be another lesson next week when we're going to cover the remaining commands we haven't covered. Believe it or not, we've covered almost every major command now, and pretty much everything you would actually realistically need to know. There's not really anything left we've not covered that I used in my Chibi Akima's development, but we are going to do another lesson next week. After that, I'm going to start progressing on to more hardware specific things. So there will be Amstrad CPC lessons, Enterprise lessons, MSX lessons, and Spectrum lessons. And also I will be doing some global lessons where we look at true multi-platform development, how to write things that work on all the systems without any modifications, and I'll be providing you with little modules you can use yourselves that have been pre-programmed to work on all of the systems, so that you can get music and sprites and things working without any on all of these systems simultaneously, without any extra work of your own. The intention being that you can get straight to coding and just use these off-the-shelf modules, and then once you feel more confident, or once you find the limitations of those answers to your needs, you'll be confident enough to modify them or write your own modules, and it will allow you to get into game programming and make nice-looking games very quickly without having to do all of the grind of writing your own sprite routines, working out how to get sound working correctly. I don't think that should be something you should need to worry about in the early days. It's only when you're really trying to grind every ounce of performance out, every byte out, or every tick of the Z80 out, that you should have to start worrying about really, is there any inefficiencies in your sprite routines? Is there anything else you can tweak out? You should just be able to get started and make something pretty nice pretty quickly. So please let me know what you think of this lesson. If you've got any specific requests, let me know and I'll try and do them. Thanks for watching, and tune in next week when hopefully I'll have another lesson ready for you. Goodbye now.